I'm going to talk about how to build fault-tolerant software. And this is something I've been doing for a very long time. I still don't know how to do it. I still get new ideas on how to build it. And in fact, the stuff I did with Erlang was not because I was interested in programming languages. It was because I wanted to build something that was fault-tolerant, and that's basically been what I've been interested in. And so I'm going to run through the various ideas I've had about how to build fault-tolerant software. They're applicable to many programming languages. Stuff like this is never finished. There are always new ideas on how to build that, and I'll look at some of these ideas. So I'm going to start with hardware. It's pretty self-evident that if you want to build something that's fault-tolerant using hardware, you can't just have one computer. If you had one computer and it crashed, the system wouldn't work. So, in order to make a fault-tolerant system, you need lots of computers. The more the merrier. If you had thousands of computers, the chances that they all stopped at the same time would be very small, especially if they're all completely isolated. I usually say if the probability that one computer stops in a given time interval is 10 to the minus 3 or something like that, if you had 1,000 of them, then it'd be 10 to the minus 3,000, which is a pretty big or pretty small number. So if you want to understand how to build a fault-tolerant system, unfortunately, you need to understand these things. You need to understand distributed programming, concurrent programming, parallel programming, and the laws of physics. That's rather nasty. All you wanted to do was build something that was fault-tolerant, but it leads you into these paths where you need to understand parallelism and concurrency, because you do actually have several machines executing things at the same time. So what about software? Well, I would say that software is pretty much the same as hardware. If you've got one copy of the software running on one machine, it's not going to be fault-tolerant. In order to make it fault-tolerant, you need several copies of this software running on completely physically separated machines. And you also need to understand the hardware story. Building a fault-tolerant system isn't just a matter of getting the software correct. It's also a matter of getting the hardware correct. And that's right down to things like duplicated power supplies, making sure the networks aren't going through the same points, making sure that you have independence of the systems. That can be very difficult. I mean, how do you know that even though you've got two independent systems, how do you know that they're not going through the same router or something like that, which will stop the system from working if the router breaks? A lot of failures in systems are not due to the failure of individual computers. They're due to failures of things like upstream routers, load balancers, and things like that. So in order to do a complete system that's fault-tolerant, you need to look at the software, and you need to look at the hardware, and you need to make sure that everything's independent, and you have to do it very carefully. So building fault-tolerant software boils down to detecting errors and doing something when you detect an error. So if you can't detect an error, if you don't know that something's gone wrong, then you won't be able to build any fault-tolerant software. And there are all sorts of different errors. There are errors you can detect at compile time. There are errors you can detect at runtime. And there are errors that are reproducible, and there are non-reproducible errors. And these all give you different sorts of problems. How do you know that a system works? It's a difficult problem. It's kind of a philosophical problem. Let's just look at the philosophy. Can we prove that systems... It'd be very nice if we could prove that systems are correct at compile time. I don't believe that's possible. Or do we believe that systems will never be correct we'll never be able to prove that they're correct. And we're going to observe some sort of error. That's going to be observed at runtime. Something's going to go wrong with the system, and then we'll detect that fact and correct it in some sense. And I believe the latter. We can only in a very limited sense prove that software is correct. The areas in which we can do that are very limited. If you ask yourself about correctness, you have to say, well, software is correct with respect to something. So the software would have to be with respect to a specification. But the specification itself might be incorrect. So at best, proving things is actually proving self-consistency. It's not proving absolute correctness in any sense. So I think that software is going to have errors in it. Especially large systems are going to have lots of little errors in them, and we have to detect these errors and do something about them. I think the analogy of a biological system is more relevant than a mathematical system. We should think of large software systems as biological things that can go wrong, and that there should be correction mechanisms to put things right. Right. And software failure is around us all the time. It's unfortunate that this is the case. I was just thinking, I mean, has anybody managed to have an application running on the internet or an app on their phone that's actually run for more than a year without it requiring an update? Has anybody managed to run a router for more than 2 weeks without having to reboot it? Anybody? You've run a router for more than a year? Goodness, what was your router? I mean, I just don't believe that this is the case. The software, we've actually evolved to a state where the software is far more complicated than we have the ability to analyze and understand it. And so what we do is we just reboot these things. Yesterday, my Sonos system, I was listening to the radio and it kept stopping. And I thought, oh, I know, I'll reboot the router. It's a fiber access. Should run at 100 megabits per second. It needs rebooting about once a week, and sometimes I forget to reboot it. And this is I'm a professor of computer science, so of course when my neighbors say my system doesn't work, and I say, well, have you tried rebooting it? And they go, no, I didn't. And they say, well, trust me, I'm a professor, reboot your system. And they reboot their system, it works fine. This is actually not part, the shortcut to getting a PhD is, when you have your viva for the PhD and you say, why should you give me a PhD? And you say, well, how do you make a system work? And you say, well, have you tried rebooting it? And they say, yes. And then they give you a PhD. I mean, that's the shortcut. So, as I said, proving the self-consistency of small programs will not help. Even if we understand how small things work, when we take a lot of small things and connect them together, they will exhibit behavior that is very difficult to understand. And proving small things is very, very difficult. So I don't know, just an example of that is to prove the Gollancz conjecture. Has anybody heard of the Gollancz conjecture? It's also known as the Ullum conjecture, Katumi's problem, Thwaites conjecture, Hass's algorithm, and the Syracuse problem. But you're probably more used to seeing it as the 3n+1 problem. And the 3n+1 says, if you've got some value of n, well, if it's odd, replace it by 3n+1. And if it's even, replace it by n divided by 2. And the Gollancz conjecture is that this process will eventually reach a value of 1. And Paul Erdos says mathematics may not be ready for such a problem. So this is an example of a very simple algorithm that despite many years of work, there has been zero progress on. We don't know how to prove that this is correct. So if you imagine a little while loop, while n is not equal to 1, n is 3n plus 1 if odd, otherwise n divided by 2. We can't prove things like that to be correct. And this is an intrinsic property of mathematics, if you like. Right in the middle of seemingly normal mathematics are little black holes of complexity and things that we can't prove to be correct. We may believe them to be correct, but we can't prove them to be correct. So even though we can prove that small things are correct, we can't prove that assemblies of small things are correct. Right. So I want to give you a little bit of background. This is a timeline of my interest in fault-tolerant systems. And it goes back to, well, I can't even see these things, so I should have to come here. This is better. Right, oh, that's much better, yes. So in 1980, I got a job working at the Swedish Space Corporation, building Sweden's first satellite. And satellites are kind of interesting. It was a Viking satellite because if you get the software wrong, that's it. And you can't upgrade the software or anything like that. All you know is the launch date is in my case, about 3 or 4 years after I started the project. So the software had to be ready before we launched the satellite. And if there were any errors in the software at all, the mission would fail. So that was the first time I started thinking about how to build fault-tolerant systems. And then in 1985, I got a job as a computer scientist in a lab in Ericsson. And at the time, Ericsson programmed all its systems in a language called Plex. And we wanted to make something that was better than Plex. The same as Plex, only better. The key requirement there was that it should be fault-tolerant. Ericsson built telephone exchanges, and there was a requirement of a downtime of less than 4 minutes a year. So we wanted to build these systems subject to downtimes of less than 4 minutes per year. If it was more than 4 minutes per year, there was a penalty clause in the contract, so we started paying fines. And it should be remembered that a long time before the internet even existed, the telephone companies have built planetary-wide communication systems. So there's considerable experience. Starting in about 1974, Ericsson made its first digitally controlled telephone exchanges. And these had the capacity to do the communications for a whole continent or subcontinent. And so by 85, by 1979, 1980, Ericsson was making systems that would control the telecommunications in an entire country. And this is way before the internet had even been thought of. In 1986, I managed to combine some ideas from functional programming with object-oriented programming and sort of unify these two fields and add concurrency to functional programming. And that was Erlang. And that proved to be pretty successful. It's worked out very well, actually. Didn't know it was going to work out that way, but about half the world's mobile communication networks are controlled in Erlang, and a significant proportion of the internet messaging system, things like WhatsApp, are written in Erlang. And that's doing, I don't know, something crazy, 20 billion messages a day. Ericsson-controlled smartphone networks the data setup paths are all written in Erlang. And that's probably controlling about half the world's communications. And that's all written in Erlang. By 1998, there were several products done in Erlang. And then an interesting thing happened. Ericsson banned Erlang, and that caused Erlang to become open source indirectly, because after it was banned, we kind of wondered what to do about that. And the answer to that was to try and make Erlang open source. If Ericsson were not interested in using it internally, then perhaps it could be used externally. So we managed to get it released as open source. And just after it had been released as open source, 4 days after, the people who developed Erlang all left by a strange coincidence and formed a company to see what we could do with Erlang outside of Ericsson. And yeah. So then, from 98 to 2002, I worked in this company called Bluetail, which I'd formed. And the emphasis of that company was to build fault-tolerant systems. We built fault-tolerant mail systems and managed to sell them. That was pretty successful, and we were bought up by Altium Web Systems, and Altium Web Systems were bought up by Nortel, and then I got fired, which was kind of fun. Yeah, and then I went to the Swedish Institute of Computer Science and became a computer science, I mean, a sort of, I think I'd say, inverted quotes, proper computer scientist. Not that I was an improper one before then. I started doing a PhD in computer science in 1986, so I was a rather slow student, but then various things got in between. And so then I went back into research. I wrote a thesis on how to build fault-tolerant systems. And then 2004, Erlang had been unbanned, so I went back to Ericsson and stayed there. And then I became a professor at Stockholm Technical High School. And then they put me out to grass and retired me in 2015. And during that period, I think when we started, this view of, there are two models of concurrency. One is a shared memory concurrency, and the other is message passing concurrency. And everybody believed in shared memory concurrency. And that kind of model of computation ruled the world. And I didn't believe in that. I thought, no, this is completely wrong, because if you share memory and something crashes, it's not fault tolerant. So I wanted memory message passing concurrency models. Message passing concurrency, this is like Tony Hoare and CSP. The world is made of very small processes that pass messages. And actually, this is the basis of object-oriented programming. Alan Kay, who coined the term object-oriented programming, said the big idea in object-oriented programming is message passing. It's not classes and methods. They are just abstract data types. All programming languages have got classes and methods, and they're just abstract data types. The real thing is independence and message passing. And this was, of course, embodied in languages like Smalltalk, where they talk about this model of message passing, but in fact they don't pass messages at all. These are disguised function calls or method calls with a syntactic device that hides that. So Smalltalk actually gets concurrency wrong. It also views everything as being an object, which I also think is wrong. There are all sorts of things that aren't objects. I mean, time isn't really an object. Failure isn't an object. Scalability isn't an object. These belong to different worlds. At the same time, there was another model of computation, actors, Carl Hewitt's actor system, and that was based on the idea of small processes that exchange messages. Not the same as Tony Hoare's CSP. CSP was, in my view, wrong because it broke the laws of physics. CSP said that synchronous communication is possible. Well, synchronous communication is not possible because there's a ray of light in between, and that takes time to propagate. You know, two sides of a thing cannot instantaneously communicate. If you're sending messages between things can go wrong. It takes time for the message to propagate. The message might not be received. It's a fundamental problem. There are certain fundamental problems in distributed computing. If you send a message to something and you don't get a reply, you don't know why. One of two things can happen. Well, several things can happen, of course, but the two major things that can happen, there can be a failure of the communications network between the two things, or the computer that you are communicating with does not interpret that message and doesn't send you a reply back. Now, you don't know if the remote computer has failed or if the communication networks failed. So it's a fundamental problem. There's no way around it. There are all sorts of things in sequential programming that are trivial and they are impossible in distributed programming. And the other way around, there are some trivial things in distributed computation that are impossible in sequential programming. And you have to bear in mind these two things. Right, so this was my satellite, Viking. It was Sweden's first satellite. And it was great fun. It was great fun. Right. So when we build fault-tolerant systems, of course, all systems don't have to be fault-tolerant. There are highly reliable systems which do have to be fault-tolerant. Nuclear power plants, things like that. Air traffic control, I guess. Perhaps, you know, if you were making nuclear missiles or something, you want to make sure people can't hack into them. Things like driverless cars, perhaps not as good as nuclear power plants. I mean, they're only going to kill one people if they collapse, or one or two people. They're not going to kill 1 million people. So they don't have to be super fault tolerant. Pacemakers, things like that. You'd be a bit annoyed if you drop dead because the software in your pacemaker is incorrect. Reliable things, yeah, it kind of annoy people if they go wrong. Banks and telephones. I mean, they go wrong all the time, but you try again and they work. And then dodgy thing. I mean, a bit cross if they, you know, Netflix and these things. And then all this free stuff. I mean, you almost expect it to fail. Okay, yeah, it didn't work. I mean, why do you get app upgrades every day or every week? You know, well, sorry, the software is wrong. We'll upgrade it again. Yeah, but this version's correct. Yeah, sure. Right. Yeah. So you have different technologies to try and make these different things correct. So how can we make software that works reasonably well, even if there are faults in the software? Well, that was the subject of my thesis. And in that, I wrote down 6 things that you needed to do. You needed concurrency. Why do you need concurrency? Well, because you've got, you know, you can't build a fault-tolerant system with one system. You need more than one. And they are necessarily working concurrently. You need to encapsulate errors. I mean, it doesn't really matter if my software is completely correct, if I've proved it to be correct, but your software can crash my software. Well, it's not very good. The objects in the real world are isolated. So if I were to take this computer and smash it, it wouldn't affect who else has got a computer. You've got a phone there. It wouldn't stop your phone from working. You know, if we can isolate things, we can make them fault tolerant. I mean, if I drop dead, you're not all going to drop dead, hopefully. Of course, sorry? It dropped, yes, it does. If I drop dead because the nuclear bombs hit us, you know, then we'll all drop dead at the same time. No, we won't. No, there'll be a slight propagation delay. I mean, I might drop dead. Yeah, physics, yes. I mean, the people who are nearest to the bomb will drop dead a millisecond before. No, not even a millisecond. A few hundreds of microseconds. No, what's the speed of? I don't know. No, but maybe the roof collapses and we'll. Yeah. Is it? How long is it? Okay. Right. Yeah. It's an experiment I don't want to do anyway. It's. If faults have occurred, we need to detect them. If we can't detect that a fault has occurred, we can't do anything about it. Code upgrade. I decided I'm only interested in systems that live forever. My systems, once started, should run forever. You never stop them and restart them. They just evolve like biological systems. And you need some kind of stable storage. Stable storage is there in case we crash, or in case one of the nodes crashes. After we've crashed, we'll go back and look at the stable storage and recover the state we were in. So some kind of method to this. So the method for making fault-tolerant systems says, what does it say? It says identify all errors, and crash, actually. I'll say more about that later. And if you can't do what you're trying to do, try and do something simpler. And handle errors remotely, not locally. Why remotely? Well, if I fell over and had a heart attack, somebody else would have to run in with a defibrillator and try and fix me up. I couldn't do it myself because I'm dead, or I'm sort of lying there unconscious. If you think of a computer system, if your computer crashes, you can't expect it to recover itself. You have to expect somebody else to do the recovery for you. So it's a very inbuilt idea that we don't try and do error recovery locally. We try and do it remotely. Of course, you can do a little bit of error recovery locally if you can get away with it. And then identify the error kernel. The error kernel is that part of the system which must be correct. When you're designing a system, it's helpful to look at the entire system and say, well, this part must be correct, and the rest can have errors in it, and to try and make that as small as possible. Typically, the error kernel, well, in the Erlang system, the error kernel is actually very small. It's maybe 500 or 600 lines of code. It's in a module called ring 0. And yeah, mainly ring 0, which I wrote many years ago, back in perhaps 1990 or something. It's never been changed since then, I think. I mean, this code is so straightforward that you know, it would be you can't prove it to be correct, but you can stare at it and think, yeah, well, that should work. I don't think there are any errors in it. Once you've got that bit right, the rest of it can be incorrect. So the error kernel's job is to sort of put yourself into a safe state and restart things. Basically, it's rebooting things very rapidly. Right. And then another idea that's built into the system, due to a guy called Peter Högfeldt, is the notion of a supervision tree, where we build systems from hierarchies of processes. Let's see if we can. So where's the pointer? There's the lasers. Can you see? Yeah, up. There we go. So these little blue things at the bottom, they're doing work. And if they fail, this failure is detected by some kind of manager, these red things. And it's their job to either restart the things under them, and failing that, if they can't restart the things, if that doesn't help, they themselves might fail, and something higher up in this tree will have the responsibility of trying to fix the error. And of course, if we can't fix it by the time we've got to right up the top, then the whole system won't work. And basically, as you go up in this tree, you're trying to do simpler and simpler things. So if you can't do what you want to do, just try and do something that's simpler. This idea is pretty common in operating systems. For example, if you open a file in C or Perl or Python or Ruby, anything like that, and if your program crashes, the operating system will close that file for you. The state of the file may not be known, but it will certainly close the file for you. So the next program that comes along can open that file. It won't put the file in a state where it can't be opened, although it might be in an unknown state. And in fact, you could have different semantics. You could have the semantics that if you open a file and the program crashes and doesn't close the file, that you put the file back to what it was before you opened it in the first place. And most file systems don't do that, but you could do that if you wanted to, and that would put an invariant into the system that would make it easier to program. Usually that's not done. People will do that in a different layer. They'll do it in a database or something like that. Right. These ideas of building supervision trees and of using message passing have been adopted. They started life in Erlang, and they've crept into a lot of different languages. So frameworks like Akka for Java and the concurrency model in Scala are directly adopted from the Erlang model of computation. It's just a picture of an Erlang system. Erlang's actually much more like an operating system than a programming language. If you look at the size of the runtime, most programming language runtimes aren't very big. The Erlang runtime is pretty big because it's emulating an entire operating system. You don't need much from the operating system. In fact, if you run Erlang on a Zen kernel, you can boot Erlang in a millisecond or so and from cold and service some web requests and then go back to sleep. And you can do all this in sub-millisecond times. So you've got everything you want to build systems. So OTP is just a library on top of that. It's a little application operating system. And all this stuff works pretty well. It's been used all over the place. The biggest applications are WhatsApp. Outside Ericsson is WhatsApp. Ericsson uses it, as I said earlier, for mobile communications. And there are various other things. Erlang found the Higgs boson, or rather, Higgs boson was found using CouchDB with a database written in Erlang. REAC is a sort of planetary scale database, which actually replaced the UK Spine database. It was an Oracle database, which was replaced by an open source database, which is quite kind of nice. Let's see. So now I'm going to talk about errors. What is an error? How do we discover an error? What do we do when we hit an error? So what's an error? What's an undesirable property of a program? It's not really a good definition of what an error is. Something that crashes your program, that's an error. Often we don't, these days, we often don't have specifications of programs. We don't have a specification and the code, and we don't prove that the specification and the code agree with each other. In limited cases, we do. I think if you're building a highly reliable system, you would want to have a very good specification and try and establish a correspondence between the specification and the code. And you have a deviation between the desired behavior and the observed behavior. So this is various types of error. So who can find the error? Well, the runtime system can find an error. How does a runtime system find an error? Well, you try and do something that's legal. Maybe you divide by 0, or you, if the day of the week is supposed to be from 0 to 6 in some number system, maybe suddenly a 7 occurs, or a 492, or 42. It's some value that's incorrect. The runtime system discovers a value that's incorrect. Or the compiler finds the error. What sort of errors do compilers find? Well, they find consistency errors. They say if you've defined this as a string somewhere and you try and add a number to it, that will fail. And this is a consistency error. And of course, different languages take different views of the desirability of this. So for example, in JavaScript, JavaScript will happily add integers to strings and not view anything strange about this. And Haskell will complain bitterly and tell you can't add integers to strings. Right. So the runtime errors can be all sorts of things. The question is, what do you do when you get an error? Well, you could ignore it. Just ignore it. Just forget it happened and carry on. I don't think that's a very good thing to do. I've got my examples later on will show you what happens when you just ignore an error and carry on. You could try and fix it. I put no there. I changed these slides. First of all, I wrote no, and then yesterday I wrote yes, you should try and fix it. And then I wrote no again. So why would you not try to fix it? Well, something's gone wrong. Quite often if you try and fix things, you actually make matters worse. you don't fix it. So basically I'd say just kind of reboot the system. Now that works with big systems. I tell my neighbors if something goes wrong, reboot the system. You tend not to do that, and I'll explain why later, in software systems, because rebooting is something that takes a long time, and the granularity of that reboot is big. I mean, the smallest reboot you can do on a complete system is to reboot the operating system. That could take a large number of, 20 seconds, or a minute or something like that. Rebooting an individual process on a regular operating system might take seconds if its recovery is good. Rebooting an Erlang process is going to take microseconds, sub-microseconds. I would say crash immediately. Bang! Just stop. Don't make matters worse. If you've run outside this domain where it shouldn't happen. What do we do when the program gets into this point where the programmer cannot imagine what's happened? I know. So don't make matters worse by correcting it. What you should do is log that error so that people can see it later. Right. What should the programmer do? This is what the runtime system should do when it sees an error. What should the programmer do? The programmer is writing the program. You're writing sort of switch this, and you go, oh, what happens if none of those work? So the programmer is actually writing the program. So they could ignore it. No, I shouldn't do that. Log it. Yes. If you've got some point in your code where something shouldn't happen, just put it in a permanent log file so you can fix it up later. And then try to fix it, possibly. You might make matters worse. Crash immediately, yes, very good. So here's where we all think wrong. In a sequential language with a single thread, crashing is not recommended. If you've only got one process and it's doing everything, then you lose everything if it crashes. So now I have to talk about concurrency. So what's the big deal about concurrency? Well, this is just a diagrammatic representation of a system that has a single process. So this is your entire world. You've got one process, one huge big process. It is doing everything, and it crashes. And so what happens when it crashes? You got there. Nothing. You've lost the entire world. So you would make enormous efforts to make sure that program does not crash. That's called defensive programming. About a third of all code in C is defensive. It's to try and stop you from crashing. That's the only purpose of that code. Okay, now imagine you've got a concurrent language. If you've got lots of processes, there we go. So we've got lots and lots of parallel processes. They're all doing things. And let's assume that one of them crashes. Okay, so here's our concurrent world with lots of little processes running around, and one of them crashes. Whoop, there you go. Did you see it? Yeah. Which one crashed? If I back it, you'll see. There. You see the one that crashes. Look. Whoop. There you go. There it crashed, and there it came back again. That's difficult to see. So in Erlang, there's a notion of remote propagation of errors. So let's draw this is a programming abstraction. It's called a link. And the link I can represent as a dotted red line. So programs that are linked together I can show diagrammatically like this. And the semantics of a link are that if the red process dies, then the blue processes get sent messages. That's it. It's not more complicated than that. It's a form of remote error handling. It says if I die, then some specific processes in the system are going to be informed. And we set these links up when we build the system or when we program the system. So for example, I might set a link to Larry, and if I die, it'll be Larry's job to run over and save me. Should we try? No, probably not. Fortunately, I'm not intending to die here. So that's remote error recovery. And of course, that makes it much easier. Your view of the world is going to be a bit different if you're programming it that way. Imagine, how would you make a reliable delivery service? Yeah, well, you could have a very fast car, a Ferrari or something like that, or you could have a bulletproof wagon or something, just can't stop. You have one of them, and you give it the job of making deliveries. But everything's going to go wrong if that one thing stops. Or you could have hundreds and hundreds of little cars all sort of beetling around at once, and you give them the job of delivering stuff. Which is going to be more reliable? Well, the hundreds and hundreds of little things whizzing around doing things. So the basic philosophy of an Erlang system is not to have one thing that does everything. It's to have a lot of small things that are all trying to do the same thing. So if some of them fail, the other ones will do it. And we just set all this stuff going, and it will work very nicely. Yeah, the blue processor sent error messages if the red process dies. So why concurrent? Well, there are several reasons why things should be concurrent. This one I've emphasized a lot, and that is that fault tolerance is completely impossible with one computer. But it's not the only reason. Once you've okay, so scalable is impossible on one computer. There's a little footnote. You could scale something up to when you've sort of filled the one computer up with computations. But over and above that, you need 2 computers, you need 3 computers. If your architecture is such that you can easily use many, many hundreds of computers, then it's scalable. Now observe that when you are analyzing your system, when you're breaking down your system into an architecture, that in order to solve your problem and make it fault tolerant, you have to make the pieces small and independent. And that is the same architecture that you need to make it scalable. So in fact, scalability and fault tolerance are very, very related in the sense that the architectures they support are the same. But it's not the only reason. And security is really difficult on one computer. I added this a couple of days ago when this the latest bugs were found in the Intel processors. I tweeted and said, it's a shared memory problem. I said, no, you haven't understood anything. Yes, I have understood something. It's shared memory. The kernel is sharing memory with the user space through some illegal back channel. It's shared memory. I mean, if you've got 2 isolated computers, it's going to be much easier to make it secure. I mean, my banking system, which I use back home, I can go in on my computer, and then I have a little handheld device that asks me to enter a PIN code. And I put a card into it, and I enter a PIN code, and then I transfer the PIN code to my computer. And that's pretty secure in a way. I mean, how could an intruder... The way I communicate is a number appears on the screen. Sorry, I have this little handheld thing with a battery in it. A number appears in the display there, which I transfer to the computer. So how is a bug going to get in there? Well, you'd have to have one of these Internet of Things devices that's spying on you, and it would have to do, and it's a one-off PIN code. Just making that device secure is much easier than making my computer secure. And that, incidentally, has had no firmware upgrades since it was given to me. I mean, it's 4 years old, and they don't release bug fixes every week to say, oh, sorry, guys, we got it wrong security-wise last week, but trust me, the latest version has no bugs in. Because it's only a tiny little device. It's probably secure. So when you've done this architecture to make things independent and isolated, you've made it possible to make it fault tolerant, you've made it possible to be scalable, you've made it possible to be secure, and, there's another reason actually. Actually, I only want one way to program systems. If you think about it, the way we program one system and the way we program planetary-wide systems is different, and it shouldn't be different. If we are doing an internet application where we have different computers involved, if I've got a computer in Poland talking to a computer in Sweden or America, there's no shared memory. There's no API where I can synchronously call things and link them together. They are in different spaces. They send messages to each other. Those messages take time. They might fail. So why should I use two different ways of programming? You know, when I program the thing inside one computer, why should I program that in a different way to when I program it when it's on 2 computers or 10 computers? I want one way of programming that is always the same. And if I've done that one way of programming, then I can take my application that runs on one machine and just split it onto multiple machines. So this is actually pure object-oriented programming based on message passing. Detecting errors, right. So where do errors come from? There's all sorts of different errors we can have. Arithmetic errors, unexpected wrong values, wrong assumptions about the environment, sequencing errors, breaking the laws of physics or maths. Shouldn't do that. Right, so these are a few errors, silent and deadly errors. The program doesn't crash, but delivers an incorrect result. Ooh, and then the noisy errors. These errors cause the program to crash immediately. Right. So here's my favorite, or unfavorite class of silent errors. Quiet, not a numbers. Do you know what they are? Yeah, they're horrible, aren't they? So, I'm just trying to find this out. Here's a nasty. Now, is that going to play that? Yes. Oops. There we go. That's a silent error in the program. Oh, there we go. There was that line there, which was wrong. It's Ada. Very nice. Right. So why are they silent? Because the programmer doesn't know there's an error. So I was kind of researching silent errors and errors and things, and came across something called Rump's Royal Pain, which is very nice. There's a formula there, which you can see at the top. And you might ask the question, suppose you're a programmer and you have to write a program to compute that. How would you know that your program gave the right answer? Sorry, how much longer have I got? Sorry? 10 minutes. Good. Right, have to speed up slightly. So if you use 32-bit precision, you get a certain answer, 1.727. If you use 64-bit precision, you get pretty similar answer. If you use 128 precision, you get things. Actually, they're all wrong because the answer is negative if you compute it absolutely correctly. It doesn't even get the sign right. Arithmetic is actually pretty damn difficult to program. It's a very nice. You should watch this if you look at the slides later. Watch that video. It's great fun. It's about an hour long. It's probably better spent time watching that for an hour than listening to me for an hour, because it's really good fun. And it's got a lot of examples of getting arithmetic right. The problem with arithmetic, if it matters, you'd have to prove every line correct if you're using floating point numbers. And that's very, very difficult. It's actually a research problem. We're going to say most programmers think that A plus brackets B plus parentheses B plus C is the same as brackets A plus B plus C. If you try it in a few different, try it in Python and I didn't try it in Perl. Probably Perl would get. I wouldn't get it right. Hopefully, so they were different. Right. Yep. Value errors. Program doesn't crash, but the values computed are incorrect or inaccurate. So how do you know? I don't know. Difficult. How do you know? I mean, programs don't have specifications. A lot of programs don't have specifications. How do you know if they're incorrect? And even if they've got test suites, how do you know that, how does that help? I have, on several occasions, been bitten. I've downloaded software. Oh, this looks good. It's got a big test suite. Of course, when you write programs and test suites, and you publish the program will pass the tests. Otherwise, you would not publish the program. I mean, that's your sign that something's gone wrong. I remember many years ago, when I was a young programmer, some guy was talking about hardware, and he said, programs learn to pass their test suites. So what do you mean? And he said, you should always be writing more tests. Because you see, if you've written a few tests, and you've written your code, and if the two differ, you tend to write the tests first, and then you write the code. And if there are any errors, you correct the code, until you get to the point where there aren't any errors. So in that case, the program has actually learned to pass these tests. Does it mean that the program is correct? No. It meant that it's learned to pass those tests. You have to be writing more tests all the time. And in fact, you've got to go beyond writing unit tests and things like that. There's property-based testing, and there are various theorem-proving techniques which are more powerful than property-based testing, which can be applied to programs to find all sorts of errors. Amazing good stuff, actually. Right. Oh, here's some little errors. If the programmer doesn't know what to do, I just believe we should crash. You see, you wouldn't think this way if 5 minutes, goodness, I should have to speed up. Right, so what do you do when you receive an error? Maintain an invariant, try and do something simpler. I'm going to finish with a little, is that all we have to do? Well, no. If you think about it, I'm saying that we should build systems from communicating processes. This just represents a couple of processes, and the red arrow represents a message going between the processes. And we tend to ignore what's inside these methods. I'd really like to draw it like that. Wait a minute, there, whoops. Okay. So if we expand this red arrow, make it a bit fatter, that's what's inside the arrow. Inside the arrow is a protocol. It's a set of messages going backwards and forwards between two endpoints. And the funny thing is that how you program inside these endpoints, inside these black boxes, there are hundreds and hundreds of programming languages that you use to program what's going on inside the black boxes at the ends. And there are very, very few languages that specify what's going on in between. And there are very, very few ways of describing these messages. If you think about it, how would you describe a message between two systems? Well, you can use XML with a schema. You can use JSON. JSON doesn't normally have schemas. It's supposed to be, in quotes, self-describing, although what that means, I don't know. You can use something like ASN1, which is a slightly better system. And you can use these proto-buffers and things like that, which give you a specification. But they just tell you the structure of the packet. They do not tell you the order in which these messages should go. APIs aren't much better for describing these. If you have remote procedure calls described in terms of APIs, you might have an API that says against a file system, you can open a file system and you get a handle back, and then you can do a read call with the handle, and you get some data back, and you can close the file. That will not tell you that a program that says open a file, close the file, read the file is illegal. It's perfectly legal. You know, the type system will tell you that that's a legal program. Well, in fact, there are better type systems. There's something called session types, which can be used to describe this. So while there are, I would say, several thousand programming languages and few dozen, maybe 20 programming languages in common use for programming what happens inside the black boxes. There are very few programming languages and descriptive technologies for describing what goes on in between the process. If anybody wants to do research into programming languages and things, don't go and do research into the ways of connecting things together. Right, so protocols are contracts, and contracts assign blame. The normal way we think about systems are clients and servers, which in principle should be able to connect, change either the client or the server without changing anything else. And I think that's not easy to do that. So I would like to see something describing what happens in between the client and server. And I'd like to add a contract checker that is just sitting there all the time, making sure that the client and server obey the contract. If you can do that statically, that's great. People use things called session types to try and do that. In general, it's rather difficult, but it can be done dynamically. And if you can do it at low cost, that's very good. This becomes especially important when we start daisy chaining several things together. If we've got several hundred or several dozens of things, it's very important to know which of these has failed. If I'm watching TV at home, I'm watching Netflix or something like that, and it doesn't work, I don't know if it's between my TV and my router. I don't know if it's between the router and my ISP. I don't know if it's between the ISP and the content distribution network, and they don't know where the error is. So we build these systems, and we're not checking all the time to identify where the errors are. The reliability of these systems is complete rubbish. Compared to the reliability we had with physical devices, it's terrible. The devices we make today work beautifully and are amazingly good if they work, but they don't work reliably over long periods of time. And one of the major reasons of that is we don't know why they fail or where they fail, and we don't monitor all this stuff. You need to do that. So you need a contract checker just sitting there watching everything, ready to pounce if something goes wrong. And I would say the big question for people to investigate is how do we describe these contracts? And I think that's actually the last slide. Yes, it is. Yes, so thank you. And I finished on time.